Hi guys, again I am doing a presentation, a video, and this time it's about friction and Newton's second law. Now I am kind of disappointed about the quiz last Friday. Some of you did really well, but others actually did really poorly. So I just want to make sure that I do this video and I mark all the forces, now this time including friction, and since there's a video, I don't think I have to repeat everything over and over and over. So yeah, so let's do it. So there is a block resting on an inclined plane, and as you can see, the inclination is given as 30 degrees. Mass of the block is given as 2 kilograms. First of all, let's mark all the forces. So I start from a center point right over here, and then I want to mark the first force, and straight down, this is what we call weight, and sometimes students write it as Fg, and then here I have it as W, and it equals to mg. We all know that. Since the block or the mass is resting on a plane, meaning it is in contact with a plane, therefore we have to have the contact force. One of the contact forces present there. Well, first of all, let's deal with the normal force, and the normal force must be perpendicular to the contact surface. And as you can see, there is a string or a stretched wire attached to the block, and we have to mark the tensional force pointed away from the mass, and I call this Ft. In addition to this, since the friction is present, I have to mark the frictional force as well. So when you look at this system, you can decide the direction that the block is going to move or about to move. And if you use your general knowledge, you will see, or you will understand, the mass or the block is about to slide down. I mean, there's no way that it will slide down as long as you have the rope attached to it, but the tendency is to go down. If it is the case, we have to mark the friction in the opposite direction of the tendency to move, and I call this Fs. Now, why did I use the letter Fs? The little f stands for friction over here, and then the S stands for static. So you have a static friction present going against the direction or the tendency to move direction. Okay, so the next thing that you need to do is to figure out the x and y axis. I am going to discuss all different xy axes for this case, because when I was going through the quizzes last week or Friday, I found out some students are still working with the traditional xy coordinate system, which is this, and then some, actually majority, were using the xy coordinate system or the xy axis, x along the plane as in this form, and then y perpendicular to the form, perpendicular to the x-axis or perpendicular to the plane as shown in here. And very few set of students are using the rotational coordinate system. Now, when they rotate the coordinate system, what they have done is the following. They have made Fn pointed in the y direction, and when you rotate so that the Fn points in the traditional y direction, you have the tension, since it is perpendicular to the normal force, that is pointed along the negative x direction. As a result, the static friction force in this case, that also will point in the negative x direction, and the gravitational force, if you rotate, it will actually point in a different direction like this. So this is W equals to mg. Now, as I started saying, this was done by a very few number of students in the class, but this is totally fine if you know what you are doing. So the one that I mentioned in the class is to have x along the plane and y perpendicular to the plane, right? So I will actually go with what I said in the class, which is the second picture, and now I am going to mark all the forces according to the coordinate system that I defined as my xy. So the normal force points along the y direction, and then the tensional force points in the negative x direction. You know what, I'm going to use the same color coordinates so you won't really mix things up. And then the friction also points in the same direction. Instead of drawing the two arrows on top of each other, I am going to draw it separately so that you see the two separate forces nice and clear. And then here I have the weight acting directly downward. There were a lot of errors on this. People were marking the weight in other directions. As I always say, that may happen in other planets, definitely not on Earth. All right, so let's work with the second picture, and I am going to take the same picture first. I'm gonna highlight that using green, and I'm going to take this green picture to the next page and have the force table set up. Now what about the traditional x and y? Now if you use the traditional x and y, here's how your normal force would look like. I am going to draw the traditional x and y on the picture here, on the above picture, and then this is how it looks like. Okay, so here you have x and there you have y. Now I am drawing the normal force in this form, and then your ft, oops, let me find it back. Okay, your ft, that is the tensional force, points in a direction like that, and then your friction also points in the same direction. Sadly, I am using two arrows, but it should actually lie on top of each other. I do not want to cover one arrow by the other, so I am using the same I am using two different lines, but note that the angle it makes with the positive x-axis is the same, and then only the w, the weight, is pointed in the negative direction of y-axis. So here is the second method. So if you ask me what I prefer the most, well, I would say the middle picture. The middle picture is what I prefer the most, and the difference between the middle picture and the rightmost picture, the yellow highlighted one, the difference is minimum. There's hardly any difference, but unless you know what you are doing, I suggest not to use the yellow force diagram over here. But there is no difference actually between these two force diagrams. And my least favorite one is the first, the traditional x and y coordinate system over here. That's mainly because you see that normal force, tensional force, static frictional force, they all have different angles with respect to the positive of x-axis. Only one is along y-axis, so the y-axis, negative y-axis, which is the weight, and that's the only one where you can find the angle pretty fast. However, the middle picture, if you look at the middle picture, normal force is right along the y-axis, tensional force is right along the negative direction of x-axis, making the angle 180, and the same for the static frictional force. And the only thing that you have to work a little is with the gravitational force down here. Now, since I am going to the other page, I am not going to spend more time on these force diagram. So I am basically going to the next page, and I take the middle picture with me, and then I will mark all the forces, all the angles over there. Okay, here we go again. You can see I have taken the middle force diagram to this side, and then I start with the x table. So here I have the normal force. Please note this nice and neat. So here I have Fn marked, and then down here I have x to represent that the x contribution or the x component of normal force. And now I am going to stick with the x and y axis that I marked on the plane. Those are the non-traditional xy planes, right? So here I have Fn angle is 90 with respect to the positive of x-axis. There you have cosine 90. Cosine 90 is a 0. Therefore, the contribution of the normal force on x direction is a 0. And then the next force is, let's say, mg. Now the component, x component of the weight would be mg. This is how we learned writing the components under chapter, I believe it's chapter 2. Yep, so it's mg, and then the angle with respect to the positive direction of x-axis, right? So here's the positive direction of x-axis, and then we start measuring from here to here. It's a 90, and here it's a 270, and this little angle is a I'm sorry, this is a 270, yeah, and this little angle is a 30, and altogether it is 300 degrees. So you have mg. Okay, I'm going with the red again, coordinating with the color, changing everything. So mg cosine 300, and cosine 300 is a half. So you have mg times 0.5 over there, and if you want to substitute for m, you can do that. I think we took it as a 2 kilogram, and g is a 9.8, and 0.5 multiply it by 0.5, and then you're all set. And then I am going with the tension, that would be ft, and then the corresponding angle, again going with the black, is a 180 with respect to the positive of x-axis. So you have it ft cosine 180. Cosine 180 is a negative 1, so you end up with ft times negative 1 would be a negative ft. And then the last is the static frictional force fs, and you take it as fs, again the same angle as in before. So you have fs cosine 180. Cosine 180 is a negative 1. So here you have the times. Fs times negative 1 gives you negative f sub s. So here we have all the x component forces. So if you write the sum of fx, Newton's second law, sum of f along x direction equals to mass times acceleration x direction. You start with the normal force contribution, which is a 0. Then you go with the weight component, mg times 0.5, and then you go with the tension, that would be a negative ft, don't forget the sign, and the last is the friction, negative fs, that equals to mass times acceleration, and this acceleration is the acceleration along the x direction. So if I just mark the direction of the equations used, that would be along the x direction, not the traditional form. So here you have it shown differently, that pointed along the plane downward. So here I have all the forces, sum of forces along x direction. And then if you want to set up the y table, now it is pretty easy. Here I go with the y table. All what you do is changing the above cosines into sines and then rewrite them. So the normal force would be Fn sine 90. Sine 90 is a 1 and you end up with an Fn here. And then the mg, forget if just to give me a second here, Fn, and then here you have y. And then the weight component along y direction, that would be mg, that is the magnitude of the force, and then sine 300. Sine 300 is a negative 0.86, and then here you have mg times negative 0.86. And then you have the tension Ft along y direction, and that would be Ft sine 180. Sine 180 is a 0. And then you have the static frictional force, and there you have Fs sine 180, and the static friction contribution along y direction would be 0. So here's the y table, there's the x table. Don't say think that these are velocities for any reason. As I saw in the quiz, some students actually had it as marked as velocities. These are force tables. And then I'm going with the Newton's second law along y direction now. So here I have some of, okay, let me just separate these things. And then here you have sum of Fy equals to mass times acceleration y. Just like last time, I am going to draw the actual direction of my equations application, because these are all vectors. And then sum of Fy, you take the normal force contribution all along the x direction, that's an Fn. And then weight contribution along y, that is mg negative 0.86, and then no contribution of the tension along y and no contribution of the static friction along y. So there you have it all, and then that equals to MAY. For any reason understated otherwise, you don't use AX and AY to be 0. So in this case, you saw that the block is attached to a string and the block is not moving. As a result of that, AX and AY both are zeros. If it is not the case, you cannot use AX and AY to be 0 using the equation number 1 and 2. You have to find out AX and AY components. Now the most important thing here is finding the normal force, because if you guys remember from the last class, Fs, maximum static friction force, FSM max, is mu sub s times normal force. Now how do you find this normal force? That is a question. So in order to find the normal force, you can use the equation 2 here and then plug the numbers for AY, and if you know AY, you can plug the number for that, and then you can find the normal force over here. And note that Fn is not equal to mg for every case. Okay, so I want you to go over this video and come to the class on Monday. I start from here. Okay, see you on Monday.